Okay, we can start now. I posted the link of our collab notebook in the chat. You can click on it on open and we can start now. So before we start with lecture 3, uh, we have covered node embeddings in lecture 2, that how the goal of node embeddings is that if some nodes are near in graph, then we would like to learn the embeddings for those nodes. And if we want to visualize them in, let's say, like n-dimensional space, then that node embedding function should have closer embeddings in that space for those nodes which appear together in the graph. And continuing on the same idea, once we have the node embeddings, uh, we can, and let's say if there is some label associated with those nodes, then we can use first neural networks and like basic feed-forward neural networks, and next is vanilla graph neural networks, which we can use with the node embedding data to solve a classification problem. And in lecture 1 and 2, we looked at that graph extends beyond simple connections. So there are nodes and edges, both have embeddings, and those features could be anything. So for example, uh, when there was no node embedding, we learned on the go with walks. But what is possible is that in some, let's say, some physical problem, let's say molecules or chemistry data, which can be represented through graphs, each node can be like one atom having different attribute, let's say molecular weight or atomic weight. So yeah, at atomic weight. So those features can be used as node features, and incorporating this data for graph machine learning models, we can get high quality embeddings, and these features can be used to classify the nodes. So what we can have is like each node, let's say if we ignore the connectivity information, the adjacency matrix, and just try to classify them based on the value of those embeddings, we can still use that data in a feed forward neural network, like we'll see it in the next cell. And then we will try to use the adjacency matrix to transform those embeddings into more insightful embeddings and see how including the graph structure can help us improve with the prediction problem. So for this tutorial, we have 4 data sets. So initially, I'm covering the Quora, and the Facebook page-to-page data set. And these are some of the toy problems which people used to benchmark their uh, new approaches to graph neural networks. And Quora is a citation network graph with around like 2,700 publications, and each publication belongs to one of the 7 classes. And there are some around like 5,400 edges between those nodes. And if let's say some of the papers cite some of the other papers, then that citation link is considered as an edge here. Next graph is Facebook page-to-page dataset. It's like it's the largest graph among all the 4 today what are going to discuss. It's about 22,000 Facebook pages and about 170K connections. And the links between different, so each page is a node, and the links between these pages capture interactions or social interactions based on the activities on the Facebook platform. So, and these graphs are so big that they cannot be visualized using the normal network X library in Python. So I got it from the book which mentions these graphs, or the research papers which mention these graphs. And these are sophisticated ways to plot these graphs, but the visualization gives us a good sense that how complex these graphs are, and if graph machine learning can work really well on complex graphs. Okay, so in summary, we if we compare these two, can just make it bigger now. So let's say if we let's say if we compare these two new graphs, the Quora and Facebook page to page graph with the Zachary's Karate Club graph we saw in the previous tutorial, we see that there's like huge magnitude of difference between based on the number of nodes and edges in classes. So since our approach worked really well on Karate Club graph, the whole idea for today's tutorial is that is graph machine learning scalable to bigger graphs, and then we'll look into that. Okay, so before that, we need to have install this PyTorch geometric library, and let me run this. Yeah, so we'll use PyTorch geometric to load the graphs because these graphs are provided in like well standardized format to load and do some graph learning on them. And we'll use this torch geometric library for that. Okay, once it installed, what we can do is use the dataset class and from torch geometric to import these two datasets, the planetoid and the Facebook page to page. So this planetoid class has the function for downloading the Quora dataset. And these graphs are bigger, but they are not that big. So it's like we can still use them and train them on a CPU. We don't really need a fancy GPU to run these graphs. And let's say that, so since it downloaded the Quora graph, since there is only like one graph here, we can extract that. And so for this Quora dataset, what we can do is run different functions, which would tell us that, okay, how many nodes are there, what's the feature size of each node, and how many classes are there in this dataset. So we can print these, some kind of like description of that graph, which tells us that there's only one graph, the bigger ones. This one is the Quora dataset, and each node is one research paper. Each node, so there are about 2,700 nodes, and each node has a feature size of 1433. Next, we will download the Facebook page to page dataset. And similarly, can print all the attributes associated with this graph. So we have one graph in the Facebook page to page dataset, and there are about 22,000 nodes, and each node has a features vector associated with it with size of 128, and there are 4 classes. And initially we saw that in the Quora dataset there are no loops, but in the uh, Facebook dataset we have loops or like self loops here. Okay, so yeah. Okay, so and this is an additional information that Facebook page to page dataset does not have any training, evaluation, or test. So we can create training, validation, and test dataset based on the number of nodes. Okay, so before we go to graph machine learning, we need to set up a baseline that how traditional machine learning models perform on these datasets. And since each node has some embedding associated with it, for example, since there's like about 2,700 nodes in the Quora dataset, each node has one embedding with associated with one label. So for now, we can assume that there is no graph structure and each node is independent and it has a label associated. So this turns into a tabular classification problem where each row is one sample and there is one label associated with it. So we can use a simple multilayer perceptron to classify this. Yeah, so once we have the data frame available for Quora dataset, what we can do is write a simple multilayer perceptron model. Yeah, and then we can, so the ideal way to have some metrics from scikit-learn, but just for demonstration purposes, we can code our own metrics here. Accuracy, which just compares the actual predictions, the true value with the predicted value, and takes an average for all the data points in our validation and test. Okay, so a small example on how to code up a multi-layer perceptron in PyTorch is that we start with the input dimension here. Okay, and then we have like one hidden layer which defines the hidden dimension here, and then that hidden dimension is connected to the outer layer. And since we have a multi-class classification problem, we have this log softmax function to convert the largest into probability values, since it's a multi-class classification problem. And we define our loss here as the cross entropy loss, our Adam optimizer. And then we can set our number of epochs, how many we want to run. And before going to the first epoch, we just put all the optimizer gradients to 0, and then we get the forward pass just by using the data out in the model. We define the loss, we calculate the accuracy, and then we put the back propagation here with the loss function here, and then the optimizer takes a step to optimize the weights. Okay, and at every 20 epochs, we can plot out the function here. Yeah, so let's run this. And okay, so what we can start, we can make our MLP, our multi-layer perceptron, with the number of features, which were around 1400. So that would be our input features. We are having 16 as our hidden features, and there are 7 classes in. And once we initialize the MLP class here, so it tells, so once we print the model for MLP, it says you have 1433 input features. You have one hidden layer with 16 units, and that hidden layer is connected to one final layer with 7 units, since there are 7 categories for Cora dataset. And now, once the model and data is done, we can run the fit function. And for 100 epochs, it just trains very quickly. And then we can see that it started with the validation 40. The accuracy was like 12%, and as it trained, it reached to 54 and kind of saturated. Okay, and so the training was done on the training set. We have this validation to probably pick the best hyperparameters. Now, since we have our own test set here, we can see what's the accuracy here. And once we run this, it's about 53%. So this was an example of running a multi-layer perceptron on the Cora data set, where since we have a multi-layer perceptron, we don't worry about uh, the connectivity or the similarity between nodes. We are treating each node individually here. Okay, if we do the same multi-layer perceptron on the Facebook page-to-page dataset, we can start with the number of nodes. We again keep the hidden size as 16 and number of classes as 4. And see, we do the same training steps here. Okay, and again, same number of epochs, 100 epochs here, and we see, okay, our validation accuracy is about 75%. And then once we try to run this on the test set, we see the test accuracy for MLP is 75%. Okay, so by using a multi-layer perceptron, we set our baselines for the Cora and Facebook page-to-page dataset. Now we can go and learn about how we can have our first graph neural network, and it's the vanilla graph neural network, because it's the most simplest kind of graph neural network, where we use the adjacency matrix to tell the model that there are some connections between the nodes, and that's how it learns to identify that there is a graph structure available in the data set and how it can be utilized to make the predictions better. Okay, so before we code, we can recap from our previous lectures that there are node features in adjacency matrix, and each node has a feature vector associated with it, and that's our feature matrix. And the adjacency matrix is just like a representation of a graph, where if there is an edge between nodes 1 and 2, then we can say that in the adjacency matrix we will have number one, like the number one as one of the entries, and where uh, the nodes do not connect, we put the entry in the adjacency matrix as 0. And since it's given here that for undirected graphs the matrix is symmetric, but maybe it's possible that in some cases you have an undirected graph, so there could be like directionality associated with your adjacency matrix in form of, let's say, values 1 and -1. Okay, so now the operation what we will define is that what we do is just multiply the adjacency matrix with the node feature matrix. So initially in the multilayer perceptron, what it was learning, it was a weight matrix which was getting multiplied with the node features. So what we initially do for graph neural networks is that multiply the adjacency matrix with the node matrix, and now this resulting matrix is computed as a weighted sum of features for adjacency nodes. So this is what basically it's doing, is that for each element in row I, this is combining all the nodes uh, connected to that specific node and weight it based on the connection strength, because we have a weight matrix which we will learn. Okay, and so this is the uh, graph operation defined, which uses adjacency matrix here. The next is aggregation, that once you have multiplied the uh, adjacency matrix with the feature matrix, how do you aggregate those information from the neighbors of each node? So in this aggregation operation, it aggregates information from different neighbors for each node. And what this means is that the feature vector for each node is like a combination of its own features and its node. That's what basically we want to learn in a graph, that since one node is connected to other nodes, then the label of one node is influenced by the other nodes, and using the adjacency matrix we can learn this information. And in some words you can say that this aggregation is like the fundamental idea behind graph neural networks, that it allows the model to learn from each node's local neighborhood, that whichever nodes are connected to that particular node influences its or contributes to the classification of its label. Okay, and why this makes a GNN? So this was the question I had when I was learning this, that how just multiplying by the adjacency matrix makes it a graph neural network, that if we do this over and over again, it can learn to classify, so the model can learn to classify nodes based on the features and the broader structure of the graph. So for example, you can define this as like for each node, since the neighbors contribute information, if you do it like one or two more steps, then you can have like higher order information uh, joining in for each node, and that's why each node can have this sense of what structure is available in the graph. And some examples for it is like, for example, in like protein networks or a social network, where if there are some connections and if you follow one person, then it might be a possibility that if they are following someone, then you may also follow them. So these are some examples from social network and biological networks. And how does feature propagation happen? Is that since we multiplied by the adjacency matrix, it propagates and updates the node features. So instead of just using the raw node features, once you apply the adjacency matrix to the actual features, the node features get updated in each layer. and the node features gets updated in a way that it kind of learns the the notion of connectivity in the graph. And if you repeat this for more iterations, it can learn information from its immediate neighbors to larger graphs based on how deep your network is. So there's like a small change based on, so for example, if we had uh, the normal multi-layer perceptron here, so how does it change to a graph model is that you have the input dimension and then you have the output. But what you do is that now we define this multiplication, the matrix multiplication operation, that you take the adjacency matrix, multiply it by the features, and then return the the learned matrix, which will get updated because we have multiplied the adjacency matrix with the input feature matrix. So this is like the most simple example of a graph neural network layer. Now to test this approach on our Quora and Facebook page-to-page dataset, what we need to do is extract their adjacency matrices. So from Torch Geometric provides us this function that we can construct our adjacency matrix here. Yeah, so right now we can see that like this, it runs the Facebook page to page and we get one example of the adjacency matrix. And let's say just to make sure that we have the correct adjacency matrix, we can just look at the shapes of these matrices. And since adjacency matrices are like node by node x node, so and then we can see that in adjacency for the Quora data, we had 2,708 nodes. So this is verified here. And for adjacency for Facebook page to page, we had 22,000 nodes in the Facebook page to page dataset. And that's the dimension for adjacency for Facebook page to page dataset. Now we can use this vanilla GNN layer. It's the same, that first we, instead of a multi-layer perceptron layer, we define this vanilla GNN layer, that we have the same input data set. We define a hidden dimension for this, and this is our first layer. The layer 2 would be that we use the new features which are embedded now in the hidden dimensional space, and now it's connected to the out, which was 7 for Quora and 4 for the Facebook page-to-page dataset. So this is our uh, so this command sets up the layer. Now we can define the forward pass, that you start with the feature vector, multiply it with the adjacency, and then we have this ReLU activation function. Uh, and then it after this activation function, it just goes to the second layer, and which is connected to the final. So this is our final layer, and then what we do is do a softmax operation. Since this is our final layer, that's why we don't have a ReLU after this. Now we just have the softmax as the output. This is our forward pass, and similar to our multi-layer perceptron, we define the loss as our cross entropy loss, because this is a multi-class classification problem. We have this Adam optimizer with some learning rate, and we can define that uh, this is the output, and based on that output, it first calculates the loss, what's the accuracy and training, and put the loss using this backward function to do backprop. And after doing backpropagation, after calculating all the gradients, the optimizer takes a step to change the weights of this model. And that's the test function works, is that first we say that now we are in the eval mode, because we are now testing that data set on our test data. So let's say we run this, and now we'll see an example that how so for in this cell we set up our vanilla GNN for our Quora dataset. It starts with 1433 features. Our out features are 16. And then this is our second layer. And our after the second layer, the out features are 7. So in terms of the setup, it's very similar that initially our MLP for Cora also had the same setup, that input feature 1433. We had a hidden layer with 16, and then there was output with 7 nodes. And similar thing is the same for our graph neural network. But once we run this, we can see that, okay, how much does it change? So, and now the Cora test accuracy is 75%. So initially when we had simple multi-layer perceptron on Cora test data, we had the test accuracy where, since there is no graph structure for multi-layer perceptron, we had about 53% accuracy. And now in using a graph neural network, we are using the graph structure of the data set. So we have our, so the test accuracy using a GNN on Cora has increased to 75%. We can do the same, we can run the same vanilla GNN on the Facebook page-to-page dataset. The input, hidden, and output feature remains the same as the multi-layer perceptron. Once we run this for 100 epochs, yeah, since Facebook page-to-page data is like the larger one among all of our data sets, it might take some time to run. Yeah. Meanwhile, if you have any questions, please let me know. Till it's running, we can move forward and see what's next coming up. So for this next part of the tutorial, we are now considering other graphs which are similar. So for example, we have a CiteSeer dataset here. It's a citation network graph where nodes represent academic papers, and then each link is one citation given to other paper. Then we have a similar dataset, the PubMed dataset, but this is specifically scientific papers related to diabetes from the PubMed dataset. And this, I provided a small table here which compares all the 4 datasets, which 2 of which we have already covered, and then 2 of which we will cover now. So, and then I just compare it with the Zachary's Karate Club graph, which we had last time. You can see that again, these 2 new graphs are like very heavy in or larger in terms of nodes and edges as compared to Zachary's Karate Club. And these are like already given as in standard format. So if somebody develops their own or a new graph neural network, then they can test these problems out to see how good their model is. And we will be using these 4 data sets probably for the next 2 tutorials as well, where we cover graph convolutions. Okay, so yeah, this one is still running. It has reached 60 epochs. Yeah, 40 more epochs remaining. Yeah, we can also observe that using a graph structure, the model also trains better, even if the number of parameters are same. So for example, even for training the MLP on the Facebook page-to-page dataset, the maximum we got was like 79% training with the same number of parameters. But since we have better embeddings learned, the model trains better with the same number of same number of parameters, and it's about 84% now for training. If we train more, probably it will overfit, but right now we can just restrict it to 100. And so it's done training now. We can test this graph neural network on the Facebook page-to-page data set with its test set. And we see it's yeah, about 82.67%. So initially for the multi-layer perceptron, we had about 75% for Facebook page-to-page. But since we have learned better embeddings using the graph structure, we have the same number of parameters in our model, but now we are getting 82.7. So this tells us that using the graph structure, if available, the model, so graph neural networks can learn better embeddings and takes care of the the knowledge bit in the graph, and then it can use that graph knowledge to predict the class of each node. Okay, moving on to the next two data sets, we can download the CiteSeer and PubMed using the functions previously provided. Okay, here we again try to access the CiteSeer graph, print the attributes associated with CiteSeer, and now we download the PubMed graph and have the attributes associated. So all of these four were classification problems, but let's say in case you have a regressor value associated with each node, then that's also possible that you can also do node regression using a similar approach. In that case, just the loss function would change. Okay. Yeah, so now similar, so we will have the multi-layer perceptron on CiteSeer and see how does it perform. So first we will have multi-layer perceptron CiteSeer and PubMed. We'll train this MLP model on both of these data sets, and then see how does simplest graph neural network perform on CiteSeer and PubMed. So start with our CiteSeer data set. Each node has a feature embedding of 3702, and then there is some label associated with each node. We start with the same, we have the same number of hidden layers, some number of classes, and we define MLP for CiteSeer. Okay, so now once this model is trained, you can say it gives us 52.7% accuracy for this multi-layer perceptron CiteSeer on its test set. We can call this our MLP class to train our PubMed graph and see that, okay, it reaches some value 70, but then starts overfitting here, and then because train is now reaching 100%. So we can test this and it just gives us 71%. Now, so using an MLP, we were able to set up like baselines for these problems and then see if our using a graph neural network can improve on it. So similar to Cora and Facebook dataset, we will create the adjacency matrices for CiteSeer and PubMed. Okay, again, we will like to validate if we created them in the right order, that the size is actually the like a square matrix of the dimension is same as the number of nodes in each data set. For sites here, we will define the vanilla GNN as like the same number of features as input, 16 in the hidden layer, and then the number of classes here, which is 6. Now we'll train our GNN for 100 epochs for sites here. Okay, and then now we can test our GNN on the sites here, and now we can see that the test accuracy has improved to 65% when we use a GNN, and which was initially was about 52% here for sites here. So from 52, it went up to 65. So now we can go to our last data set, which is the PubMed, and Can define this vanilla GNN on the PubMed dataset. We can train it now. Again, it might take a while because it's a bigger one. Since it's still training, yeah, please let me know if you have any questions. Yeah, for the GNN and PubMed, one observation we can make is that for Epoch 20, the train has reached 100%. We had the same case for vanilla MLP that it reached 100, but that time for validation, the accuracy was 65% here. But one indication we can get from this training is that for 65 was increased to 78 just because we have a better network and better embeddings learned after each layer using the graph structure.
There's a question in the chat.
Yeah. Okay, what exactly is the GNN predicting? Node connection features. So each node has a feature, is each label associated with it. So let me go back to the first data set which we had. So let's take this example of Quora data set. There's 2,708 nodes. There are 5,429 edges. And then each node, since it's a publication, there is one topic associated with it. So each citation or each publication has topic. Let's say, what field does it belongs to? Let's say one could be belongs to like computer science, another could belong to biology, but there could be some papers which are based on both. So for example, if we visualize this, each node is one paper and each node has one label associated with it. So you can say that, okay, how many clusters you can find is like this one big uh, connected component where each node connects to each other, but then there is like this component here, the smaller one, which has a similar structure to the bigger one, but there are cross uh, connections between the communities. So each node has some label associated with it. Yeah, so each has one class. So it's just uh, like a multi-class classification problem. Same with for your Facebook page to page dataset. Okay, can you have like some more examples? Like for example, our uh, this sightseer dataset. So if I provided that for each node, there are 6 classes, where each representing a different topic or field within academic papers.
Mm-hmm.
Yeah.
So if a paper mentions 2 or 3 fields together, it will just probably.
Yeah, so then you can have like a multi-label classification thing. Yeah, so I think then the prop formulation changes, but the basic idea remains same, that you can still use the graph structure. Yeah, for PubMed, like you can have like there are 3 classes which categorize the papers based on different types of diabetes research. So let's say there could be some papers like type 1 diabetes, another class could be like type 2 diabetes, or another could be like some other kind of, I think there's another one more type, gestational, I guess. So there could be like based on 3 classes of diabetes. Yeah, I hope that answers your question.
So when it's determining the accuracy, does that
Yes,
mean that it's taking in some type of adjacency matrix
yes.
and then predicting what features are going to be associated with each node based on that adjacency matrix?
Yeah, so that's true. That's what we were discussing here, that using this adjacency matrix, the model learns that some papers are connected to, or like some, for example, in the citation graph, some papers are connected to each other. And that helps the model to learn better embeddings so that, let's say, if two nodes are connected, we can assume that they may belong to the same field. And so then their labels should be similar.
Okay, that makes sense. Thank you.
Yeah. So because in the multi-layer perceptron, which is just like a feed-forward model, we do not have this notion of connectivity between different rows or different samples. So the MLP just considers each paper as one individual example. But in GNN, we are telling the model that there is some structure associated with these nodes or these papers, and use that to make your predictions better. Yeah, I think yeah, here. Yeah, so for PubMed, it ran for 100 epochs. The validation gives us like 17, it just saturated after epoch 60. And once we run our PubMed, the graph neural network model on the PubMed test set, we get 65. So in summary, what we did today is we had two approaches. The first one was multi-layer perceptron, which is a simple feed-forward model, which considers each sample as have it's individual, doesn't have any connections to other samples. And then we have our graph neural network where we provide the adjacency matrix to tell the model that there is some graph structure associated and you have to learn from it. And then we saw examples of four data sets, the out of which three were citation data sets and another was a social network data set composed of Facebook pages. And in summary, what we saw is that all comparing the MLP, the feed forward neural net versus the GNN for all those four data sets, we can see that GNN gives you like a higher outperformance for these problems, which tells us that graph neural networks are extremely powerful in understanding the graph structure wherever available. Yeah, that's it for today's lecture. Thank you.